Hello everybody, and welcome to our video on directional derivatives and the gradient vector. So far, we've considered derivatives in the x or y directions, but we may want to consider derivatives for some arbitrary vector. So in other words, if we're traveling along some path in an arbitrary direction, what would the rate of increase or decrease in our z values be? So if we look at this model here, we see we've got our vectors in the y direction and the x direction here. And this red vector is at this point on the curve, and it's just heading in this arbitrary direction. Yeah, I think it's actually heading at like 45 degrees from the x-axis, but just pretend it's arbitrary. So the idea here is just how do we analyze the behavior of this function on arbitrary directions rather than just along the x or y path? So, well, that's what we call the directional derivative. So definition, the directional derivative of f at x naught, y naught in the direction of a unit vector, u equal to the vector ab, is d sub u of f, so that's our notation for the directional derivative of f with respect to u, equals the limit as h goes to 0 of f of x naught plus ha, y plus hb. That should just be f of x, not x naught. All right, a little typo, got that fixed. So f of x plus ha, y. Oops, actually, both of these should be knots. Well, that's off to a good start. Excellent. I love finding typos right when I get started. Okay. There we go. So f of x naught plus ha, y naught plus hb minus f of x naught, y naught. So because we have this direction vector a and b, the amount that your x and y coordinates are changing is dependent on that vector. So that's illustrated here by the ha and hb. So h decides how much your vector is being influenced, how much you're moving away from x naught and y naught. And so that's, of course, happening in the direction ab. So this is basically our normal limit definition for a derivative. It's just requiring that the change in our input occurs both on x and y at the same time. So if that limit exists, that's what we call the directional derivative. Now, our key theorem here that's going to allow us to compute these things fairly easily is that if f is a differentiable function of y and of x and of y, then f has a directional derivative in the direction of any unit vector u equal to the vector ab. And the directional derivative of f with respect to u is given by the partial derivative of f with respect to x times a plus the partial derivative of f with respect to y times b. So let's just take a look at the proof here. So the proof's a little tricky, and we're going to use a pretty common approach. So you would have seen an approach not that dissimilar to this in, proving like the mean value theorem or Rolle's theorem, something like that. So that proof would be that we first start by defining some new function, and then we're going to analyze that new function and determine the result on the original function, f here, based on that. So we're going to define a function of h called g of h, which is equal to f of x naught plus ha, y naught plus hb. So here we're treating g as just a function of h and as everything else as constants. So then by the definition of the derivative, if we take the derivative of g at 0, that's the limit as h goes to 0 of g of h minus g of 0 over h. All right, so if we plug in these values here, well, h stays the same. And then when we plug in 0, we get f of x naught, y naught over h. So this is exactly the formal definition of the directional derivative. So far, so good. Right? We've seen that g prime of 0 here is equal to the directional derivative of f with respect to u. Okay, so now let's also express this function g of h equal to f of xy. So now we're treating these two functions as being equal, where x is x naught plus ha, and y is y naught plus hb. All right, so we've got this function g of h is equal to f of xy, but x is just this whole expression in this first coordinate, and y is the whole expression here. So the chain rule for the derivative gives us that g prime of h should be equal to df dx times dx dh plus df dy times dy dh. Well, what does that give us? Well, df dx and df dy are by definitions the partial derivatives of x and y respectively. Now if we look at dx dh, well, x is x naught plus ha. If we take its derivative with respect to h, you just get a. And likewise, dy dh, if you take its derivative with respect to h, you just get b. So as to say, g prime of h is partial derivative of f with respect to x times a plus the partial of f with respect to y times b. So if we set h equal to 0, then what do we get here? We get that x and y are going to be equal to y naught. And so g prime of 0 based on this formula gives us the partial of f with respect to x at the point x naught y naught times a plus the partial of f with respect to y at x naught y naught times b. So what have we shown here? That g prime of 0 has to be equal to the formal definition of the directional derivative, but also g prime of 0 is equal to this expression. So if these two things are equal, then the directional derivative at this point is equal to this expression involving the partial derivatives. So not too crazy. All we've done here is just figured out two different ways to express g prime of 0 based on our definition g of h equals this function. And as a result, we've shown that those two expressions give us this theorem. So this is going to be much more convenient because obviously in general, calculating derivatives with these limits are pretty cumbersome. So we try to avoid it whenever possible. And thankfully, that's a lot of the time. Okay, so side note, if the unit vector makes an angle of theta with the positive x-axis, then we can express it as the vector cosine theta sine theta. So we've been using that for a while. And that allows us to rewrite this unit directional unit vector derivative in the following way. duf equals the partial with respect to x times cosine of theta plus the partial with respect to y times sine of theta. And more often than not, well, I don't know if I should say that. I should say quite often we'll end up using this form because you might be talking about, okay, I know the angle that's formed with the x-axis in the context of the problem. So my unit vector is going to be cosine of that angle, sine of that angle. And this is going to come up quite often. So definitely keep that in mind. Now, if we think about that, we can actually rewrite this directional derivative in a slightly different way. Because what is this directional derivative? The partial with respect to x times cosine of theta plus the partial with respect to y times sine of theta, or times a and times b. So what is that? Well, that's the same thing as the dot product between this unit vector and this gradient vector here. So that we're going to call this the gradient vector. So this is the vector f with respect to x, f with respect to y. So definition. If f is a function of two variables x and y, then the gradient of f is the vector function. So this symbol is called nabla, but I'm just going to say gradient of f, defined by the gradient of f equals the vector of the partial derivatives of x and y respectively. Right, and here's that with our I and j notation. Okay, so in summary, we can, if we keep this definition of this gradient vector in mind, we can denote our directional derivative as the dot product of the gradient vector of f with the directional vector, the unit directional vector. Now, the reason we're bothering to give a special name and notation to this gradient vector is because this idea of a gradient vector is going to come up, this type of expression is going to come up all the time from here on out. We're going to see a lot of situations where you have this type of vector. So it's best to just give it a name and make sure we learn it because it'll allow us to shorthand a lot of things moving forward. Okay, so let's move on to an example. Find the gradient of f, evaluate it at point P, and find the rate of change of f at P in the direction of the vector v. All right, so we got quite a lot of things there, but really it's not too bad. So the gradient of f is the vector partial of x, partial with respect to y. Okay, so if I just rewrite this function a little bit, y squared times x to the negative first, that's going to make it easier to take this partial derivative with respect to x. So we get negative 1 times y squared times x to the negative second, so that's negative y squared over x squared. And then the partial with respect to y is just going to be 2y over x. So if I want the gradient of f at the point 1, 2, that's going to give me negative 4 over 1, so that's just negative 4, and 2 times 2 over 1, so that's just positive 4. Okay, now I have v here, but remember for the directional derivative, we don't want just any old vector. We specifically want the unit vector. So we need to find the unit vector here, but u is just the vector v divided by its magnitude. So 2 squared plus the square root of 5 squared. So what do we get here? 2i plus root 5j over, this will be 4 plus 5. It's going to be 9. Square root of 9 is 3. So this is, in bracket notation, 2/3 root 5 over 3. So finally, if I want the directional derivative of f at the point 1, 2 with respect to the direction u, then this is just going to be the dot product here. That's going to give us negative 4 times 2/3 plus 4 times root 5 over 3. That's negative 8 plus 4 square root of 5. All divided by 3. Okay, so let's just think about what this number tells us, though, real quick, just to keep the context in mind. This is telling us the rate of change of the output f at this point when heading in this direction, right? Now, that's what this means. It's the rate of change in this direction of the function. Okay, so let's move on and look at our definition for the gradient of 3 variables. And it's exactly what you'd expect. We define the gradient of f of x, y, z as the vector of the partial derivatives of f with respect to x, y, and z for each coordinate here. And likewise, we define the directional derivative of f with respect to the unit vector u as the gradient of f dotted with u. Okay, so example 2, find the directional derivative of the function at the given point in the direction of the vector v. Okay, so the first thing we got to do is find our gradient of the function. So the partial derivative with respect to x is going to give me y, these will both be constants, plus z. And now the partial derivative with respect to y is going to give me x plus z, and that'll be 0. And now the partial derivative with respect to z is going to give us y plus x. So if I evaluate this gradient at the point 1, negative 1, 3, that gives us what? So y plus z, that's 2. And then we get x plus z, that's 4. And then we get y plus x, it's going to be 0. Okay, now we need to find the directional, the unit vector. So we have v. So of course our unit vector should be v divided by its magnitude. So that's 1I plus 5j plus 2k divided by the square root 1 squared plus 5 squared plus 2 squared. That's 1I plus 5j plus 2k divided by, well, this is 25 plus 4 plus 1. So that should be 30. So that's root 30. So this is 1 in bracket notation. So 1 over root 30, 5 over root 30, and 2 over root 30. Okay, so now if we want the directional derivative of u, or the directional derivative of f at this point, with respect to the unit directional vector u, it's a real tongue twister. If we want this directional derivative, then we just need to take the dot product of these two things, right? So we take the gradient of f dotted with u. And what does that give us? That gives us 2, 4, 0, dot, 1 over root 30, 5 over root 30, 2 over root 30. And this dot product gives us 2 times this, that's 2 over root 30, plus 4 times this, that's 20 over root 30, plus 0. So this is 22 over root 30. Okay, that's it for example 2 here. Go ahead and move on to another idea. So maximizing the directional derivative. So theorem, suppose that f is a differentiable function of 2 or 3 variables. The maximum value of the directional derivative is the magnitude of the gradient vector of f, and it occurs when u has the same direction as the gradient vector of f. So proof. Well, the directional derivative of f with respect to the vector u is gradient of f dot u. And we know from our theorem on the dot product that this is equal to the magnitude of f times the magnitude of u times cosine of theta, where theta is the angle between the gradient of f and u. So the maximum value of cosine of theta is 1 when the angle theta is 0, right? And that's going to be the largest value we can get, right? The magnitude of u is always going to be 1 because it's a unit vector. So the maximum value you get here is when cosine of theta is 1, which gives you the gradient of f, the magnitude of the gradient of f. And it's going to happen when the angle between them is 0. So in other words, when those two vectors have the same direction. So pretty simple idea, I think. Okay, so let's tackle another example here. Suppose that you are climbing up a hill whose shape is given by the equation z equals 1000 minus 0.005x squared minus 0.01 y squared, where x, y, and z are measured in meters, and you are standing at a point with coordinates 60, 40, 966. The positive x-axis points east and the positive y-axis points north. So in which direction is the slope largest? What is the rate of ascent in that direction? And what angle above the horizontal does the path in that direction begin? Okay, so it's kind of a whole lot going on here. So let's just take each of these one piece at a time. So in which direction is the slope largest at the point? Well, that's the gradient of z evaluated at that point. So let's go ahead and calculate first the gradient. So this should be the partial with respect to x and the partial with respect to y. And what does that give us? Negative 0.01 times x, right? Because the derivative of x squared is going to be 2x. 2 times this is 0.01. And the derivative of this is going to be 0 here. Now, when we take this derivative with respect to y, what do we get? We get negative 0.02 times y. So now if we evaluate this thing, at the point 60, 40, we get negative 0.6 and negative 0.8. So this is the direction of largest slope. And I'm fine with just using the vector as the direction. Okay, so what is the rate of ascent in that direction? Okay, so what is the rate of ascent? That's the magnitude of the gradient. Okay, so that magnitude is going to be the square root of negative 0.6 squared plus negative 0.8 squared. That's 0.36 plus 0.64. That's the square root of 1, which is 1. And so what is the rate of ascent in that direction? Okay, so if you imagine this diagram here, that this horizontal vector here, it's not the x or y axis. This is going to be the gradient of z at the point. So in other words, that means that the tangent vector here, right, is going to have this slope of 1. So the slope here, y equals 1 times your change in your gradient of z. That's really like your variable here, right? So maybe I should just write m equals 1. I don't want to get the notation too confusing here. So the slope is equal to 1. So if the slope is 1, that means we'll call this opposite and hypotenuse and adjacent. So what do we know? Well, if this is, the slope is 1, opposite and adjacent divided by each other are 1. So O over A is 1. But that's also the same thing as tangent of theta. So that means theta is 45 degrees. So the angle made with the horizontal plane, is going to be 45 degrees. So theta equals 45 degrees. All right, that's it for 11.6, or not for 11.6, that's it for this part example. We still got a little bit more. I'm getting ahead of myself here. So don't want to forget about this, tangent planes to level surfaces. So consider a surface S with equation f of xyz equals k. Recall that this is like a snapshot of which independent variable values correspond to the output k. So you have 3 independent variables and a fixed output. And then you could look at different values of k to analyze what independent variables correspond to those outputs. But this is also the same kind of equation that we get that describes certain things like spheres, so forth and so on. So recall that this is a snapshot of which values correspond to the output k. And so let's let P of x, the point x naught, y naught, z naught be a point on S, and C be a curve that lies on S and passes through P, and let P be described by the continuous vector function R of t equals x of t, y of t, z of t. Let t naught be the parameter value corresponding to R of t naught equals x naught, y naught, z naught. Okay, so P is some point on this curve. This particular point is described at this point, this vector R of t naught. Now, since this curve lies on the surface, x of t, y of t, and z of t have to satisfy the equation that we had for our surface, right? So if we apply the chain rule, what do we get? The derivative of f with respect to t equals df dx times dx dt plus df dy times dy dt plus df dz times dz dt, and the derivative of k is going to be 0. So what does this look like? Well, this looks like exactly the gradient of f dotted with the derivative of r. So r being the parametric vector equation describing our curve. So if we've got that curve and we've got the gradient of f, then we take the dot product of those things. That gives us the derivative of f with respect to t along that curve. And so what do we notice? Well, the dot product of the gradient of f with the derivative of r is 0. And in particular, just take note that since this dot product at this point is 0, keep in mind in the back of your head that this gradient of f at this point is going to be perpendicular to this tangent line here, or the vector described by this, the tangent vector described by having this derivative here. Okay, so definition. If the gradient of f at a point is not 0, then we define the tangent plane to the level surface, f of x, y, z equal to k, at that point as the plane that passes through P and has normal vector, the gradient of f at x naught, y naught, z naught. So yeah, as we said, since this dot product is 0, that means this gradient of f at this point is perpendicular to this tangent line here. And so this is going to be a normal vector to the tangent plane that we describe here. So this dot product is 0. This is true for any curve passing on the surface passing through that point. So that means that if you're imagining your curve, let me see here. We'll try to do a rough drawing. So you've got like some, say, semi-sphere here, like that. So you consider some like point on this place, and there's like a plane that's tangent to this thing. So what's happening here is that you're tracing curves along this, and any curve by any vector description of the curve, r of t, leads you to the fact that you get tangent lines that describe this plane, right? These tangent lines are going to be lines in this plane. And this gradient vector of f is always going to be perpendicular to those tangent lines. So that means that since this holds true for all of these curves along the surface, we can use this to describe the tangent plane itself. And that's all that this is here. The tangent plane to the level surface equation is just the dot product of the gradient of f times x minus x naught, y minus y naught, and z minus z naught here. Now, another thing I want to point out is that you get the normal line to S at P. by just taking x minus x naught divided by the partial with respect to x, y minus y naught divided by the partial with respect to y, and z minus z naught divided by the partial with respect to z. And this comes from the same way we dealt with normal lines before, except this time we specifically know that our orthogonal vector, our normal vector, is given by the gradient. So these are the direction components of that gradient. Okay, so let's tackle one more example here. Find the equations of the tangent plane and the normal line at the point -2, 1, -3 to the ellipsoid x squared over 4 plus y squared plus z squared over 9 equals 3. Okay, so the first thing we need to do is find our gradient, right? So keep in mind your function, f of x, y, z here, is just this left side of the expression. So the gradient, when I take the derivative with respect to x, I get 2x over 4. The derivative with respect to y gives me 2y. And with respect to z gives me 2z over 9. Now if I take this gradient and evaluate it at the point, what do we get? Well, x is -2, so this is -4 over 4, that's -1. This is 1, so I get 2. This is -3, so I get -6 over 9, that's -2/3. Okay, so, well, what's the rest of my equation of the tangent plane? That's straightforward, right? You just take these partial derivatives in your gradient and multiply them by x minus x naught, y minus y naught, and z minus z naught. So my equation for the plane is -1 times x minus -2 plus 2 times y minus 1 plus -2/3 times z minus -3. And this should all be equal to 0, right? So I'm going to clean this up a little bit. This will be -x. This is +2, but distribute the negative and you get another -2 plus 2y minus 2 minus 2/3 of z plus, that's plus 3 in here, but multiplied by -2/3. So that becomes a -2. So this becomes -x plus 2y minus 2/3 z minus 8. Okay. And lastly, for the normal line, so this is the equation of the tangent plane. So for our normal line, what do we get? We get x minus x naught over the partial derivative of f with respect to x. It's -1 equals y minus y naught over the partial with respect to y, and z minus z naught divided by its partial. So those are our symmetric equations for the normal line. And we could clean those up a little bit and just make it x plus 2 over -1 equals y minus 1 over 2 equals z plus 3 over -2/3. And I think that's fine. I'm okay with just leaving that in that form. Okay, so in summary, let's just think about some of the things we've learned here. The gradient vector gives the direction of the fastest increase of f, and the gradient vector is always perpendicular to level curves. So if we think of like a level curve map, then if you're looking at the level curves, wherever your curve is, if you draw a perpendicular there and you connect those dots, that essentially is telling you the curve of steepest ascent up your, path. Say if this is a mountain, right? If you're following the perpendicular paths along each level curve, that's the curve of steepest descent. All right, now we're actually done with 11.6. Thank you for watching.